video we're going to explain a couple of examples related to pinned homotopy between loops. So here's the sphere S2, and we've got a loop around the equator. We're going to take this little blue mark point here as being the base point in S2, and the idea is, you see, we can do a pin. It's kind of easy to do a homotopy where we take the loop and contract it to a constant loop, but here we're doing a pinned version, right? So this is a homotopy in which we move the loop, but always just keeping the base point fixed. And we can pull the loop over the North Pole and contract it down to just being the constant loop at the base point. If the base point moved, then that wouldn't count as a pinned homotopy, but because we're keeping the base point fixed, that's pinned. Now we're going to do another example with a torus. Okay, so here we're thinking about this kind of loop here, where we start at the base point here, and then we go all the way around this red loop. Okay, so actually the kind of original version here, we're going to go just all the way around the red loop, and then after we've been around the red loop, we go around the blue loop, and then we get back to the base point here. We can do a pinned homotopy of this, and notice, here's the base point. It's not moving at all. This base point is not moving. We're moving the rest of the loop, twisting it around the torus, and we end up here. Okay. So the original loop, okay, so like that, that's where we go kind of around horizontally first, and then after we've been all the way around horizontally, then we go around vertically around the blue loop. At the end of the day, after we've performed this pinned homotopy, the kind of red business, the red loop is kind of what we do first, and that's kind of, now we've moved to a situation where we should do the vertical loop first, and then after we finish the vertical loop, then we go around horizontally around the outside of the torus. And so so if we call the kind of horizontal loop all the way around the outside of the torus, we call that U, and the vertical loop kind of around here, we call that V. And what we're starting with is kind of doing U first and then V, so that's U star V. And at the end of this pinned homotopy, we're doing the vertical thing first, which is V, and then U, so that's V star U. Okay, so the conclusion of this is that U star V is actually pinned homotopic to V star U, and that's a kind of an illustration of the fact that the fundamental group pi1 of the torus is actually commutative. It doesn't matter in which order we do things. That's a very special feature of the torus. For typicals, for loops, typical loops U and V in a typical space X, then U star V is not going to be homotopic, pinned homotopic to V star U. But if this particular example of the torus, those two things are the same.